SMCITOOL is an interactive tool that has been designed to teach and learn sliding mode control. It is the result of a joint work by UPC and UNIG members. In the following, its basic functionalities will be shown. The application is self-contained and shows everything is just one screen. The interface is composed of 4 main blocks. The upper left, named Textual Definition, allows to describe the plant and the sliding surface both using text field or sliders. Joint to this, named Graphical Definition, the plant can be defined using a graphical figure. The lower left part, the control action, states and output evolution shows the evolution of most relevant closed-loop variables. The upper right part, named Event Evolution, contains a time diagram describing the events that are generated during the simulation. And finally, the lower right part, named Closed-Loop Phase Plane, contains a phase diagram that shows the sliding surface and the trajectory starting at a given initial condition. The textual definition contains 3 check buttons which can be used to define the output, the switching surface or the system parameters using text fields and sliders. If the output is selected, the output can be defined, also the desired behavior over the sliding surface. The relative degree is automatically computed, so the specification fields are automatically updated. Steady state value for relative degree 1 outputs and steady state value and time constant for relative degree 2 outputs. The graphical definition block shown a complex plane. Over it the plant poles are shown. Also the point corresponding to the B vector is shown. Both things can be modified by dragging them. A black triangle allows to modify the figure scale. The control action, states and output evolution block is composed by 2 figures. The upper one shows the control action while the lower one shows the evolution of the output and the states variables. The lower figure can be customized using the available check buttons. Time scale and initial conditions can be modified by dragging over them. Over the lower figure the closed-loop behavior can also be specified interactively. The event evolution block shows the time instance for which an event is generated during the simulation. Different colors are used for different event types. The closed-loop phase plane block contains the closed-loop trajectory and the switching surface over the phase. The initial conditions can be interactively modified by dragging them. The switching surface can be interactively modified by dragging it. When dragging the line, it rotates over the control point. When dragging the control point the line moves. This figure contains a set of check buttons that can be used to customize the figure. The equilibrium point check button allows to visualize the closed-loop equilibrium. The sliding zone check button shows the region over the switching surface where a sliding regime exists. The vector field check button visualizes the vector field direction over the phase plane. The attraction check button shows the region of attraction over the phase plane. In the following, a couple of examples will be introduced to illustrate the application capabilities. The first example is composed by a system with 2 stable complex conjugate eigenvalues. The goal is to regulate the first state component to a given value, firstly to 0.75. As the output is relatively degree 2, a convergence dynamics will be defined over the switching surface. A time constant of 0.5 seconds will be selected. SMCITOOL will be used to analyze if this behavior is possible. First, the system parameters will be introduced. The open-loop eigenvalues and vector B components will be introduced combining the text fields and the graphical editor. Second, the output will be defined. The components of vector row are introduced using text fields. As the output is relative degree 2, a desired steady-state value and a time constant need to be defined. Both values are introduced using the text fields. They could also be defined dragging the control points over the red curve in the bottom figure. After this, the closed-loop phase plane is automatically obtained. As it can be seen, after a certain time the trajectory hits the switching surface. After that the closed-loop system enters in a sliding regime. As the dynamics over switching surface has been designed to be stable and the equilibrium point is inside the region where sliding the regime exits, the closed-loop system converges asymptotically to the desired equilibrium point. Looking at the event window, it can be seen that only one event corresponding to time when the trajectory hits the switching surface is produced. Turning to the control figure, it can be seen that the control action is equal to -1 until the event is produced. From that on, the equivalent control can be shown. Using SMCITOOL, it is very simple to analyze the initial condition effect. Dragging the initial condition, it is possible to interactively update the closed-loop trajectory. While the initial conditions are within the attraction zone, the behavior is qualitatively the same. When the initial conditions leave the attraction zone, it is necessary to hit the switching surface more than once to reach the sliding regime, thus more events appear in the event figure. Moving the sliding surface has the effect of changing the equilibrium point. While the equilibrium point lay inside the region where sliding regime exists, the controller will operate appropriately. In case the equilibrium point lays outside of the region where sliding regime exists, the controller will not achieve its goal. The second example is composed by a system with two real eigenvalues, one stable and another which is unstable. The output is defined as a linear combination of the states, and the control goal is to regulate its value to -1.275. As the output is relatively degree 1, no convergence dynamics will be defined, and the reaching time will be finite. SMCITOOL will be used to analyze if this behavior is possible. First, the system parameters will be introduced. The open-loop eigenvalues and vector B components will be introduced combining the text fields and the graphical editor. Second, the output is defined. The components of vector row are introduced using text fields. As the output is relative degree 1, a desired steady state is only required. After this, the closed-loop phase plane is automatically obtained. Taking an initial condition in the attraction zone, the trajectory hits the switching surface and remains over it. As it can be seen in the left part, the output reaches the desired goal in finite time. All initial conditions inside the attraction zone provide similar closed-loop behavior, but as the system is open-loop unstable, the system trajectory might diverges and initial condition outside the attraction zone is taken. SMCITOOL is available for free and can be used by anyone interested in sliding mode control.